Okay, so this video is going to be over the second fundamental theorem of calculus. This is standard I6, page 177. These are the pages you got today. Okay, so target is students will apply the second fundamental theorem of calculus using the chain rule for composition functions to determine the derivative of a function defined as an integral. So let's say we have a function. We know of all types of functions. We know of linear functions, quadratic functions, cubic functions, trig functions, all of those. And I'm going to introduce you to a new type of function. We call this a function defined by an integral. So we can simplify this function and we can actually calculate the function using the fundamental theorem of calculus just like we would if both the 2 and the x squared were both numbers. So just like with fundamental, the first thing we'd want to do is, of course, take the antiderivative. So first thing, we would get 1/2 t squared plus t, just from the basic power rule, evaluate from 2 to x squared. Okay. Then, of course, plugging in, fundamental theorem of calculus says to take our top limit and plug in for the t in this case. Sorry about that. Okay, you're not really writing this down. If you want to, write it on a post-it note. I'm sorry I didn't say that earlier. I just kind of want to give you some frame of reference as we start. Okay, and then take the bottom one and do the same thing. And get that. I'm going to simplify this out really quickly. I'll get 1/2 x to the 4th plus x squared. Those parentheses weren't really needed. And then on the other side, we'd have 4 minus 4. Once we combine our like terms. Okay, so we get a function, same exact function, process is the same, but the function started out as being a function defined as an integral. So the actual original function itself is that integral piece at the top. Now let's say, just like with everything else, we could integrate that, we could compose this, anything with functions that we can do with regular functions, we can do with this as well. With the idea that the function that we're dealing with in here, that t plus 1, is a continuous function, of course, because we can't integrate things that are not continuous as is. Okay, I can do things like take the derivative. Now, we know from the beginning of differentiation that antiderivative and derivative, those are inverse operations. So really, if I take the derivative of this function, I should get back to the original function that we started with, which is that t plus 1. Okay, so I'm just going to take the derivative of this. So f prime of x equals, if I get 2x cubed and then plus 2x. Not really the function I dealt with, but I want to factor this. I see I have a GCF of 2x. So I should get, sorry, not that. If I factor out a 2x, I should get x squared plus 1. And this looks very familiar to this, with the exception of that x squared now being in replacement of where that t is. So not exactly the same, but very similar. And if we think about this 2x, where did that come from? Because I should end up with almost the exact same thing that I started with. But if we think about it, especially at this level, what we're doing mathematically is we're composing two functions. We're having a function within a function. We're having a situation where f of g of x. Okay, we're putting a function into another function. And what we know about taking the derivative, sorry, getting those spots things again. If I take the derivative with respect to x of a function within a function, that means I have to apply the chain rule, which means I'm going to take the derivative of the outside function with the inside the same times the derivative of the inside function. So if we go back to where we started with, this really is the inside piece. So f prime of x with the inside the same times the derivative of the inside piece. So this is a result of our chain rule. Okay. And because we're taking the derivative, chain rule is going to apply there because we have a composition function, a function within another function. Okay, so the second fundamental theorem of calculus, depending on what textbook you have, depending on what proof you read for the fundamental theorem of calculus, it's broken into two parts. One being what we know already, the second part being just the fact that the derivative and the antiderivative, or the integral, are exact inverse operations, and they pretty much undo each other, with the exception of the idea of the chain rule coming into effect. So the second fundamental theorem of calculus says a couple of things. Of course, if we're dealing with a continuous function on an open interval that is containing the x value that we're talking about, if we take the antiderivative with respect to a being a number, and that's very important here, that a is in fact a number. So this is a number, okay? If we take the derivative of the integral, the derivative and the integral pretty much cancel each other out, and we get back to where we started with the exception of the composition. I get back to f of x, and that is a terrible, let me rewrite that. I get back, oh God, sorry about that. I get back to f of x, where the only thing that has changed is we've taken that x in the top and replaced the variable that was originally in our function, which was t in this case. So that's really all the second fundamental theorem of calculus is saying, is that our derivative and our integral are inverse operations. There are two exceptions. One, our g of x, if we have a function other than x, and really it applies to the first one as well, and I'll come back to that. If we take the derivative of the antiderivative, the only thing that's going to change is whatever the function is replaced into the variable. So f of g of x. But because we are taking the derivative and g of x is in fact a function, when we take the derivative, we have to apply the idea of the chain rule, which means we're taking the derivative of the inside as well. Okay. If we think about the previous one, our inside piece was x. So if we think about taking the derivative of the inside, we get 1, which leads us back to just f of x. So that's a simple one because the derivative of x is 1. Anytime the derivative of whatever that function is not 1, it changes things a little bit. Okay. Another thing we want to keep in mind is that our function must be on top for this to be a shortcut. But since we have rules that allow us to change, in fact, our limits, the first thing we could do before we take the derivative of the integral is, in fact, to change our limits by negating our integral value, pushing the a to the bottom and the function to the top, okay, of f of t dt, before we even apply the rule. So that negation is now part of the coefficient, and we know that coefficients just follow along in our process. So if we take the integral or the derivative of the integral, those are going to cancel out, and all we have to do is replace the current variable with the new function and compose it. But because again we're doing the derivative, we're always going to go back to the derivative of the inside as well. Apply the chain rule. Okay, so here are some examples of derivatives and integrals. And like I said, this is just kind of a new function, a function defined as an integral. Okay, that's what we call it. Okay. So for the first one, my function is x. Sorry, it's skipping again. My function is x right here. And I'm taking the derivative of the integral, so those are inverse operations. It's kind of like adding to and subtracting to. We're getting back exactly where we started. So we get the square root and then just the composition. And the derivative of the inside happens to be 1. We don't really need it in this case, so we wind up with just the square root of x. The bottom number is not going to matter because of the fact that we're taking the derivative. And if we plug the 3 into the square root, we're going to get the square root of 3. But the derivative of the square root of 3 is just 0. So that's going to 0 out because we're taking the derivative of the function. Okay. The next one, big problem, because our function is backwards, our function is on the bottom, the first thing we'd want to do before we take the derivative is to, in fact, negate to bring our function to the top. And we get that. Then we can take our derivative and our integral and cancel those out as inverse operations, and we still have that negative as part of the coefficient, square root, and we're just taking the function and composing it into the integrand. So x squared, but because we've composed and we have a composition function, we have to apply the chain rule. So the derivative of the inside piece happens to be 2x. Now I can definitely simplify that. We get negative, the square root of x squared gives us x times 2x, and in the end I get negative 2x squared as the simplification. So the derivative of that integral piece. Now the next one, again, all we're doing is taking the derivative of the integral. Our function's already at the top, so that's good. So our integral and our derivative are going to cancel each other out, and we're going to compose the new function. This is the one time where what comes behind the trig doesn't stay behind the trig, and the reason for that is because we're composing two different functions. We're doing a composition here. So negative sign is going to stay the same. 4 is part of that, and we're going to replace the t with the 3x squared. And then we're going to come back with the chain rule and multiply by the derivative of the inside piece. So 3x squared. So that derivative is 6x. Again, I want to simplify this out. Put that negative 6x in front. Remember that negative is part of that. And then the 6x is from here. And then sine. And then 4 times 3, we can definitely simplify that to 12x squared. And there we go. Now the last one is a little bit more tricky, and the reason I say that is because if we look at our limits, both of them are in fact functions. The higher function is on top, the lower function is on bottom. Of course, 2x cubed is greater than x. So in this case, what we want to do is to pick a value. It can be any value. I always stick with 0 because 0 is the easy number. And what I do is I actually split up my integral using one of my rules that we learned a couple weeks ago. I know I can integrate from x to 0 of 3t plus 1 dt plus the integral from 0 to 2x cubed dt. Because the 0 here and the 0 here are the same value, that's just doing that whole part plus part is equal to whole. And from here, what I can do for that first one is now use the rule that I have above to negate. Second one is fine, so I'm going to leave it. We have that. The derivative and the integral cancel each other out because they're inverse operations, and all we're doing is now composing. So negative 3x plus 1. Okay, that negative is part of the coefficient of everything, and all we're doing is taking that x value and plugging it in. We can come back and multiply by the derivative of the inside, which happened to be 1, that derivative of x, plus we're going to do the same thing here. We're going to replace the t with 2x cubed plus 1, and then we're going to come back and multiply by the derivative of the inside piece, which is at 2x cubed. Sorry, so 6x squared. From here, all we want to do is do some simplification. Distribution of the negative. And then I'm going to do some distribution and, well, I guess it all is distribution. So 3 times 2 gives me 6, and then 6 times 6 gives me 36. And then x cubed times x squared gives me x to the 5th. And distribution plus 6x squared from distributing here to here. Okay, now those terms are alike. I don't like them like that, so I'm going to put them in proper order from highest exponent. And we get that. Okay, so really the second fundamental theorem of calculus is just saying that an integral and a derivative are inverse operations and they undo each other. However, the chain rule is still going to apply there. So let's look at actually doing a couple problems where we start with a function defined as an integral. So let's start with the top one. So let's say f of x is equal to 2x squared plus the integral from 2 to x of the square root of 3t squared plus 1 dt. The first thing I want to do is find f prime of x. So all I'm going to do is take the derivative of everything from left to right, including that 2x squared. It's part of the function. We're going to take the derivative. So when we take the derivative, we get 4x plus, now the derivative and the integral are going to cancel each other out, and all I have to do is the replacement of my variable. Well, that is terrible. You can't even see what that is. Let me rewrite it. And because we're taking x and composing it, the derivative of x is 1, so I don't need anything. Therefore, that right there is, in fact, my derivative. Now, if I wanted to plug into my derivative to find the instantaneous rate of change, again, that's just plugging in a 2 for the x's. So for everywhere there's an x, I'm plugging in a 2. Simplifying it out, that gives me 8 plus. And 2 squared is 4, 4 times 3 is 12, 12 plus 1 is 13. So that gives me the square root of 13. And that's where I would leave my answer. Okay. If I want to take the second derivative, that comes back to this guy right here. So all I'm going to do is take the second derivative. So derivative 4x is 4 plus. Now the derivative of that function, well, we can use our shortcut. If you look on your pink sheet, okay, that's exactly what I'm going to use. And the derivative of the square root of u gives me u prime. So the derivative of the inside over 2 square roots of the inside. Remember, that's one of those shortcuts. Okay, I could simplify it if I wanted to. So 4 plus 3x over the square root of 3x squared plus 1. And that would be it. Now to plug in, we would just do it like we normally do. 4 plus, everywhere there's an x is going to 2. So we get 4 plus 12 over the square root of 13. Oh, sorry, not that. I messed up. That should be 6 times 2. That should be 3. So then we wind up with 6 over the square root of 13. Makes more sense. When we come into class tomorrow, we will start with this problem and then we'll talk out any questions you have. So if you have any questions, write them down and come prepared tomorrow to ask them.